Good afternoon once again, children.
Good afternoon, ma'am.
Good afternoon. Yeah, please write along with me. Children, I've shared my screen. It's visible, right?
Yes, ma'am.
Yeah. Please write along with me. I'll let you then. Now tell me, we start now to get the first result to show that AF is equal to AE equals S minus A. Okay, so we begin like this. We know that AF is equal to AE. Now express AE in a different way. AE can be expressed as
AC minus EC, ma'am.
very good. AC minus CE. Yeah. And CE can be replaced with CE is equal to
Minus
CD, ma'am.
DC, ma'am.
CD. And CD is equal to
S minus C.
sorry. CD is equal to
BC minus BD.
correct. So in bracket CD is equal to BC minus BD. Open the bracket. Now AC, BC, AC and BC, they are the sides of the triangle. We will not replace them. Now BD can be written as BD can be written as
BF.
BF and BF is
AB minus
AC minus AF.
AF.
AB minus AF. Okay. Now you need to get AF is equal to AE is equal to S minus A, semi-perimeter minus A. So semi-perimeter minus A meaning we know that perimeter is AB plus BC plus CA or AC. Perimeter of this triangle is AB plus BC plus AC. Semi-perimeter is S. So perimeter is 2S, right? Perimeter is 2S. So now here you have the sides. You can see AB here, you can see BC here, you can see AC here. But this it is not AB plus BC, it is AB minus BC plus AC. It's minus BC. See, we have AB, we have AC, we have BC, but it is minus BC. But we want plus BC. So you write whatever you want, you introduce. Whatever you want, you introduce. Somewhere the sign changed, no? While AB minus BC. Yeah, this is plus. Yeah. Now I erased, something was removed by mistake here. So children, AB plus, let me just rearrange this. AB minus, okay, plus AC minus BC minus AF. Okay, no, I think just unnecessarily that'll be an extra step. 1 second. So see here, AB, you want plus BC, right? So if you add BC, you should subtract BC. Keep that in mind. Huh? If you add BC, you should subtract BC. Why are we adding BC? Because we don't have plus BC. We want AB plus BC plus AC so that we can write that as 2S. Okay, so we have AB, we don't have plus BC, so we are introducing plus BC. We have plus AC. Now we added BC, no, so we should subtract BC. But there's already one minus BC here. Write that. And minus AF. And minus AF. So now this one is 2S. This one is 2S. Perimeter, no? So perimeter is twice a semi-perimeter. 2S minus 2BC. 2BC. And you can take the AF to the other side. AF plus AF. Bring the AF here. So you have twice AF is equal to 2S minus, what is BC given in the question, children? A. BC, look at the question. BC is A. So 2A. Now take out 2 common. Take out 2 common. In the RHS. All right. So 2 and 2 gets cancelled. So AF is equal to, we know that AF is equal to AE. AF is equal to AE. Therefore, AF is equal to AE is equal to S minus A. It will be more clear when we work the next two. Just listen to this. See, we started with AE, children. We started with AE, which was on side AC. We started with AE, which was on side AC. So we came from side AC, then to CB, and we finished in AB. So you should keep replacing. You started with this side AC. So keep replacing till you reach the third side. So AC, we started with AC, then CB, and then we finished with the third side AB. We'll work the second and third subdivision together. It will be clear, children. Finished?
Yes, ma'am.
Yeah. So next, we know that we'll have to prove that BD equals BF. We know tangents from the external point B to the circle are equal. So BD equals BF. We know we need to show that BD equals BF is equal to S minus B. So we'll start with BD is equal to BF. BD is equal to BF. Now BF is equal to children. Quickly. No, that's low. So AB minus AF. Okay, AB minus AF. Now let AB remain. AB is the side of the triangle. Let that be because we want to replace AB plus BC plus AC with 2S. So we'll have AB, will not disturb AB, the side of the triangle ABC. Now replace AF. What is AF? AF is equal to AE. AF is equal to AE. So minus AE. Now replace AE. What is AE? AC minus EC. AE is AC minus EC. So in brackets, minus AE, so minus AE is AC minus EC. Open the bracket. So here we have AB and AC. So they are the sides of the triangle. So we'll not replace them. We'll replace EC. So AB minus AC plus EC. EC is equal to CD. EC is equal to CD. And CD is equal to
BC minus BD.
BC minus BD. BC minus BD. And here we stop. So now we have AB. We have plus BC. Now we want plus AC. AB plus BC, we have plus AC we have introduced. So when you add AC, you should subtract AC. When you add AC, subtract AC. There's a minus AC already here in the expression. So write that. And then minus BD. Now this one is 2S. This one is 2S. AB plus BC plus AC is perimeter. And perimeter is twice the semi-perimeter. Semi-perimeter is S. So perimeter is 2S. Minus 2AC minus BD transpose. So it will be BD plus BD. We already have BD in the left-hand side. So BD plus BD. We already have BD in the left-hand side. So twice BD is equal to 2S minus AC is given to be B in the question. AC is B. So 2B. So 2BD equals 2 common S minus B. So BD, and we know that BD is equal to BF. So BD is equal to BF. Therefore, BD equals BF is equal to S minus B. Next one. CD equals CE is equal to S minus C. So CD is equal to CE. CD is equal to CE. Now CE is C is equal to AC minus AE. CE, CE. Don't write CE, CD. That's what we've written. CD is equal to CE. And CE is AC minus AE. AC minus AE. AE. AE is AF. AE is AF. And AF is AB minus BF. AB minus BF. AF is AB minus BF. AC and AB are the sides of the triangle, so we will not disturb them. We'll further replace BF. BD. BF is BD. And BD is BC minus DC or CD. BD is BC minus DC. BC minus DC. I'll continue here. So we have CD is equal to, we have minus AB, but you want a positive AB. We have minus AB, you need a plus AB, so we'll introduce plus AB. AB, we have plus BC in the expression already, and we also have plus AC. So we have written plus AB. So when you add AB, you should subtract AB. And there's already one minus AB in the expression earlier. Write that. And minus DC. We have added AB, so subtract AB. So now this CD, transpose it. So CD plus CD, DC or CD is equal to, this one is 2S minus 2AB. So 2CD is equal to 2S minus AB is given to be C. Take out 2 common. S minus C. Therefore, CD is equal to CE. Because CD is anyways equal to CE, tangents from the external part of the circle. So CD is equal to CE is equal to S minus C. Wasn't that easy to understand, children?
Yes, ma'am.
Very good.
Completed, ma'am.
Very good. Yeah. if AB equals AC, so the triangle is an isosceles triangle. The triangle is isosceles. If AB equals AC, prove that F. Oh, where is F? I think this should be F. Okay. Prove that F bisects BC. Okay. So we are given that AB equals AC. Now AB can be written as, children, AB can be written as? Yeah, AB can be written as?
AC, ma'am.
No. You'll have to write something for AB and something for AC.
A plus BD.
AD
AD?
Plus
plus
BD.
BD.
Correct. And similarly, AC?
AE plus C.
AE plus EC. Correct.
C.
Okay, yeah, C, correct. Both are the same, no? ECC, AE plus EC or CE. Both are the same. Okay. Now on either sides, AD and AE will get cancelled, correct? Why?
Tangents from same external point.
Yeah. Correct. Or you can replace, or instead of cancelling, you can also replace it in the next step. You can write AD plus, okay, 1 minute. 1 minute, children. Let's write off all those results so that it's easy to give the reason. See, you write AD equals AE, all the results we know, and then BD equals BF and CF equals CE. Because tangents from an external point to the circle are equal. To the circle are equal. Okay. All right. So now AB is equal to AC. AB is AD plus DB equals AC is AE plus EC. Now AD plus DB is, you can even change AD. Anything can be, replaced. So you can even replace for AD. AD is what? AE plus DB is BF equals, don't change AE. AE is AE only. Only then you can cancel that on both the sides. Plus EC. EC is CF. So now AE on either side gets cancelled. So we have BF is equal to CF. BF is equal to CF means F is the midpoint of BC, which means F bisects BC. BF is equal to CF. So that means F is a midpoint of BC, which means F bisects BC. So this implies F bisects BC. The point F divides BC into two equal parts.
Completed, ma'am.
Yeah.
Ma'am, 1 second, can you go back?
Oh, sure. Sorry. Yeah, sure.
Thank you.
Yeah. Yeah. Anyone wants to share how to go about this?
Kn is equal to Km plus Mn, ma'am. And
Correct. Yeah, correct. 1 second. Yeah, Kn is equal to, so Kn can be written as Km plus Mn. Correct. Then
Km is equal to AK. So
correct.
AK plus and Mn is equal to Bn plus Bn. Hence proved.
Correct.
Complete, ma'am.
Yeah. Now you can simply add the two results. So you must make sure that you write Km is equal to Ka, and then you know that Km plus Mn will give you Kn. Km plus Mn. So below Km, you must write Mn, the result for Mn. Km plus Mn is Kn. So write the result for Km. Km is equal to Ka. And then for Mn is equal to Nb. Now add. So Km plus Mn is Kn equals Ka plus Nb or Ak plus Bn. So you can write the two results, one below the other, carefully, and add the two results. Done, children?
Yes, ma'am.
Okay. Till in 2 minutes, I'll just come back. Please write this. Yeah, thank you, children. I'm back. Done writing?
Yes, ma'am.
Yeah. Okay. So I don't have to explain why the quadrilateral ODCE is a square. Every corner is a right angle and adjacent sides are equal, so it's a square. Which means all the sides are equal. So each side of the square is equal to R units. So this one is R, but the whole thing, BC, this part is R, but the side BC is A units. So BD will be equal to A minus R units. Similarly, side AC, here you see side AC is B units, but CE is R units. So AE will be equal to AE or EA is equal to B minus R units. I repeat. So since this quadrilateral is a square, all the sides are equal to R units, which means DC is equal to R. But this side is A units. So the remaining part BD will be equal to the whole thing A minus R. So BD is equal to A minus R. If BD is A minus R, BF is also A minus R. Because BD is equal to BF. Similarly here, AC is equal to B units. But CE is R. C is the side of the square now. So C is R. AE will be equal to B minus R. AE is B minus R. And if AE is B minus R, AF is also B minus R because AE is equal to AF. Tangents from the external point A to the circle are equal. Now, BF is A minus R. AF is B minus R. But what is BF plus AF? It is AB, which is C. This side is C. The hypotenuse is C units, which means A minus R plus B minus R is equal to C. A minus R plus B minus R is equal to C. So on working that, you get R is equal to A plus B minus C by 2. So you must note here that A and B are the legs. A and B are the legs of the right triangle and C is the hypotenuse. And R is the in radius. R is the in radius. 1 second, children. Yeah, children. So R is the circle here is the in circle to the right triangle. The circle in the figure is the in circle to the right triangle. So the in radius R is given by A plus B minus C by 2. So, like understanding that in words, in radius is equal to sum of the legs. A and B are the legs of the right triangle. In radius is equal to sum of the legs minus the hypotenuse by 2. In a right triangle, the in radius is equal to sum of the legs minus the hypotenuse by 2. Now you need to also show that it's equal to S minus C. So just proceed. You have A plus B. You have A plus B. You want plus C. So you add C and subtract C. When you add something, you must subtract the same thing. We have A plus B. We want plus C. So add C and subtract C. And there's that minus C already there by 2. Now A plus B plus C is 2S. A plus B plus C is not S. A plus B plus C by 2. S is semi-perimeter, not perimeter. S is semi-perimeter. But A plus B plus C is the perimeter. So A plus B plus C is 2S minus 2C by 2. 2 common, 2 cancels. R is equal to S minus C. So the in radius is also in a right triangle. The in radius is also the semi-perimeter minus C, meaning minus the hypotenuse. So to get this result, children, you start with perimeter of triangle ABC. See the results above that you know very well. Okay. The results from the theorem, tangents from an external point of the circle are equal. You know that well. You start with perimeter of triangle ABC. Okay. So what is perimeter of triangle ABC? It is AB plus BC plus AC. Because we have perimeter of triangle ABC in the result. So we start with that. Perimeter of triangle ABC is equal to. We start with that, meaning I'm saying the main proof starts there. This result you know it anyways. So you just like understand the answer from here. Since we have perimeter of triangle ABC in the final result, we'll start with that. Perimeter of triangle ABC is equal to AB plus BC plus AC. Now BC can be written as BF plus CF. Now further, BF can be replaced with BD and CF can be replaced with CE. Now AB and BD is AD, CE and AC is AE. But we know that AD is equal to AE. AD is equal to AE. So you can replace AE with AD or AD with AE. Both are fine. So you get twice AD is equal to perimeter of triangle ABC. So AD is equal to half. 2 comes for division to the other side. So it's half by 2. So it is half. So AD is equal to half into perimeter of triangle ABC. But we know AD is equal to AE, right? So if AD is half perimeter of triangle ABC, AE is also half perimeter of triangle ABC, which means AD is equal to AE is equal to half perimeter of triangle ABC. Since we have perimeter of triangle ABC in the result, you start from there. Perimeter of triangle ABC is equal to the sum of the 3 sides, AB plus BC plus AC. Once you start then you will know how to continue. You'll have to split BC. Yeah, and the rest just follows like that. You just need to make the right start. Done, children?
Yes, ma'am.
Yeah.
Complete.
Good. Now, I'm going to introduce you to a theorem which is not a part of our syllabus, but will be useful to answer MCQs. You can also use them for, answering 2-mark questions. Though not in the syllabus, it is accepted. It's not that if you use a concept which is not in the syllabus, you will not get marks. Nothing like that. As far as your steps and your justification is correct, you can go ahead. Okay, so this is called the alternate segment theorem. Some schools introduce this theorem to the students. Some other schools do not. So we'll see this. Very useful for MCQs. Alternate segment theorem. Now we'll not learn the statement and all that because anyways, that will not be asked. That's because it's not a part of your syllabus. So you will not be asked to state the alternate segment theorem. So we'll not see that now, but what is the result by this theorem? What should be given and what is the result that you can take from this theorem is what we're going to see now. All right. So now this theorem is based on a chord and a tangent passing through one end of the chord. Okay. So circle, any chord. So chord AB. I'll not mark it. Okay, this is B, all right? This is B. Now there's a tangent passing through B. This is B, all right? There's a tangent T. Let's call it PQ. So this is the requirement. To use this theorem, see now, you know there's a theorem called the Pythagorean theorem or the Pythagoras theorem. But when will you use it? In which situation will you use it? When there's a right triangle. In the same way, when can you use this theorem, alternate segment theorem? In a circle, if you find a chord and a tangent passing through one end point of the chord, then you can think of this theorem. In a circle, if you see a chord and a tangent passing through any one end point of the chord, then you can think about using the result by this theorem. So this is the requirement. Circle, chord, tangent passing through any one end point of the chord. So here the chord is AB. A and B are the end points of the chord. Through the endpoint B, we see a tangent. So B is the point of contact of the tangent with the circle. Now, with respect to the chord and the tangent, you can see two angles. You can see an angle here and you can see an angle here. That is taking the tangent as the line and the chord as the ray. You can see two angles formed on either side of the chord. Treating the tangent as a line and the chord as the ray, you can see two angles on either side of the chord. Okay. Now we'll take up the angles one by one. We will take up this first. Now this is the angle between the chord and the tangent on one side. Okay, so this is the angle between the chord and the tangent on one side. Now this angle passes through this segment of the circle. This angle is a part, it crosses through this segment of the circle. So for this angle, this is the alternate segment. This is the alternate segment. Segment is, what is a segment? Circle, chord. Now the chord divides the circle into two segments, minor and major segment. So this is the minor segment, this is the major segment. Major because it contains the center of the circle. Okay. So now this angle, a part of the angle crosses this segment of the circle. Okay, this is actually the minor segment. So the other segment is called the alternate segment. Now we'll see the angle subtended by the chord in the alternate segment. We'll see the angle subtended by this chord in the alternate segment. So take any point on the circumference of the circle in the alternate segment, anywhere. So see, this is the circumference in the alternate segment. Only this part, this one. This is the circumference of the alternate segment. Take a point anywhere on this part. So I've marked this point. Let me call it R. Now join AR, BR. This is the angle subtended by the chord AB at the point R in the alternate segment. This is the angle subtended by or made by the chord AB at the point R in the alternate segment. Why is this the alternate segment? Because this angle between the chord and the tangent passes through this segment, which is the minus segment. So the other segment becomes the alternate segment. Now this angle is equal to this angle is the result by the alternate segment theorem. So 1 mark, supposing this angle is given to be 70 degrees and you're asked to find this, straight away 70 and you can move to the next one. You don't have to spend 2-3 minutes working the answer, meaning using that elaborate way. You can do it. I'll tell you how to do it without using the alternate segment theorem a little later. How to do this without using the alternate segment theorem, I'll tell you. So by the alternate segment theorem, if this is 70, this is also 70. Now, I'll just repeat this. Yeah. Chord AB, A and B are the endpoints of the chord. PQ is a tangent through the endpoint B. So B is the point of contact of the tangent with the circle. The chord and the tangent, between the chord and the tangent, we can see two angles. Between the chord and the tangent, we can see two angles. One is this, the other is this one. I will take them one by one. Now, this angle is equal to some angle formed inside the circle. So which is that? Now, since this angle between the chord and the tangent passes through this segment becomes the major alternate segment. The major segment is the alternate segment. Now let's find the angle subtended by the chord in the alternate segment. The angle subtended by the chord in the alternate segment. This is the alternate segment. This is the alternate segment because the angle here passes through this segment. So the other segment is the alternate segment. Take any point on the circumference in the alternate segment, any point. So this one. Join the endpoints of the chord to that point. Join the endpoints of the chord to that point R. Now this is the angle. This is the angle subtended by the chord AB at the point R in the alternate segment. Now this angle is equal to this angle. If this is X, this is also X. Let's see the other one now. Okay, so now this angle between the chord and the tangent. This angle between the chord and the tangent. So now this angle is a part of the major segment, this segment. So the alternate segment is the minor segment. The alternate segment for this angle is the minor segment. Since this angle between the chord and the tangent passes through this segment, the other segment becomes the alternate segment. Now we need to identify the angle subtended by the chord AB at any point on the circumference of the alternate segment. So this is the circumference of the alternate segment. Take any point R on the circumference of the alternate segment. Join the ends of the chord to that point. Join the ends of the chord to that point. A to R, B to R. Now this is the angle subtended by or made by the chord AB at the point R in the alternate segment. Now this angle is equal to this angle. Angles in the alternate segment of a circle are equal. angles in the alternate segment of a circle are equal. Take down this children. Straight line, children. I'm sorry, I'm not able to get it straight. It's a straight line, it's a tangent. Done, children? Finish writing and drawing? Children, use the emoji, raise your hand. Tanya, Madhumita, Krish, Arjun, Sasham. No. Okay, children, finish writing and drawing? Yeah, Sashank.
Yes, ma'am.
Okay, yeah. Let's proceed.
Yes, ma'am.
Okay, fine. To prove that the tangent drawn at the midpoint of an arc of a circle. So circle, take an arc. So let AB be the arc of the circle with center O. Prove that the tangent drawn at the midpoint of an arc of a circle. So you can see circle with center O. Consider the arc AB. Midpoint of the arc AB. So say this one. Okay, so C is the midpoint of the arc AB. That means arc AC is equal to arc BC. The length of arc AC is equal to the length of arc BC. Circle with center O, AB is an arc. A and B are the end points of the arc. C is the midpoint of the arc AB, which means CA, the length of arc CA is equal to the length of arc CB. So prove that the tangent drawn at the midpoint of an arc. So there's a tangent through C. There's a tangent through C. It's parallel to the chord. This tangent is parallel to the chord joining the endpoints of the arc. A and B are the endpoints of the arc. So when you join the endpoints AB, you see the chord AB. You need to prove that the tangent is parallel to the chord. You need to prove that the tangent is parallel to the chord. So go down to 8th standard. How do we show that lines are parallel? If alternate angles are equal, then lines are parallel. If corresponding angles are equal, then lines are parallel. If co-interior angles are supplementary, then lines are parallel. So you'll have to use one of these to show that the lines are parallel. Okay. So construction, join CA and CB. Join CA and CB. Now, since CA is equal to CB, why is CA equal to CB? Because arc, don't write children. I'll just explain and then I'll write it. So just listen to me. Arc CA is equal to arc CB. length of arc CA is equal to length of arc CB. Now, there's a theorem which says equal arcs contain equal chords. Equal arcs contain equal chords, which means AC is equal to BC. That is, the line segment AC or the chord AC is equal to the chord BC, which means ABC or CAB is an isosceles triangle. This side is equal to this side. That means this angle X is equal to this angle. But by the alternate segment theorem, see here, this is the chord. BC is a chord, and this is the tangent, and this is the angle between the chord and the tangent. Now this angle is equal to this angle is equal to, see here, this angle is between the chord BC and the tangent. The angle which I have marked is between the chord BC and the tangent. Now, this is the segment. This is the segment through which this angle passes. This is the segment. See the circle. This is the chord BC. This is the chord BC. So the rest of this is the alternate segment. And you can see the point A in the alternate segment. You can see the point A on the circumference of the alternate segment and the ends of the chord. The chord is CB. The ends of the chord CB is joined to the point A, CA, BA. And the angle formed there is X. So this one is also X. This one is also X. The measure of this angle is X. This one is X. Angles in the alternate segment of a circle are equal. But now you see some line, transversal, and some line. Alternate interior angles are equal, X, X. You can see the chord AB, transversal BC, and the tangent here, X, X. Alternate interior angles are equal. Therefore, AB is parallel to the tangent. So this line is parallel to this line, which means AB is parallel to the tangent. Yeah, now you can write with me. I'll just come back, children. So here circle arc AB, endpoint of the arc are A and B. C is the midpoint of the arc AB. Through the midpoint C, we have a tangent MN. We need to connect the endpoints of the arc to get the chord AB. Connect the endpoints of the arc A and B to get the chord AB. We need to prove that the chord AB is parallel to the tangent MN. For which we'll have to join CA and CB. Since arc CA is equal to arc CB, C is the midpoint of the arc, so arc CA is equal to arc CB. Equal arcs contain equal chords. So chord CA is equal to chord CB, which makes triangle CAB an isosceles triangle. So the base angles are equal. We have marked them X. Now this angle BCN, angle BCN is the angle between the chord BC and the tangent CN or MN. This angle BCN is the angle between the chord BC and the tangent CN. So now this angle will be equal to the angle subtended by the chord in the alternate segment. This angle between the chord and the tangent is equal to the angle subtended by the same chord in the alternate segment of the circle. So to identify that angle which is formed in the alternate segment, see the chord BC, this is the chord BC. So this one is the segment through which this angle passes. Leave that segment. The other segment is the alternate segment. A is a point on the circumference of the alternate segment. And you can see that the ends of the chord BC are connected. See here, CA and BA. So the ends of the chord BC are connected at that point A. So this angle CAB is the angle subtended by the chord BC at the point A in the alternate segment. And that angle is X. So this one is also X. This is X. This is X because this is X. Now you see, this is the chord transversal and this is the tangent. This is the chord. This is the tangent. And you can see this is X. This is also X. Alternate interior angles are equal. That means the chord is parallel to the tangent. Is that clear, children?
Yes, ma'am.
Okay.
Yes, ma'am.
Yeah. Okay, you have to find AD. Yeah, please complete that. So in this figure, children, this angle is 90 degrees because angle in a semicircle is a right angle. See, first, what we have to do is, with the help of the information given, we should see if we can, find some more information. So look at the figure. AB passes through the center O. The line segment AB passes through the center O. So AB is the diameter to the outer circle. AB is the diameter to the outer circle. So we know that angle in a semicircle is the right angle. So see the outer circle, AB is the diameter. So angle AEB is equal to 90 degrees. The angle in a semicircle is a right angle. Also, BE is a tangent to the inner circle, but a chord to the outer circle. BE touches the inner circle at D. So BE is a tangent to the inner circle at D. The same line segment BE is a chord to the outer circle. So BE is a tangent to the inner circle at D, or to the small circle, the circle inside, the inner circle, the small circle. BE is a tangent to the small circle at D. But the same line segment B is a chord to the bigger circle. Now we know that the perpendicular from the, now these are concentric circles, they have the same center. So we know that the perpendicular from the center to the chord bisects the chord. And why is it a perpendicular first? How do we know that OD is the perpendicular? Because so treat to get, treat B accordingly. Now, when you treat B as a tangent, OD is a radius. OD is a radius to the inner circle, and B is a tangent to the inner circle. OD radius, inner circle. BE tangent, inner circle. So 90 degrees. Now look at BE as a chord to the outer circle. So the perpendicular from the center to the chord will bisect the chord. So BD is equal to DE. BE is a tangent, OD is a radius. So radius, tangent, perpendicular. So we have 90 degrees here. Now OD is the perpendicular from the center to the chord BE. So it bisects the chord. BD is equal to DE. So what is all that we have gathered? Angle in a semicircle is a right angle. So this is 90. And this is 90 because radius perpendicular to tangent. And also BD is equal to DE because the perpendicular from the center to the chord bisects the chord. Okay. So now we have any order you can write. See this proof, like there's no order kind of. You can just write it in any order. Whatever you write, you need to justify with a reason. So now in this small triangle, okay, now let me tell you how, like I have tried to find AD. This one is a right triangle. This one is a right triangle. So I started from here. See, I was just looking at a triangle which has AD. So this is the triangle that has AD, right? AD. Okay. And now this one is a right triangle. And AD is the hypotenuse of the right triangle. So if you find DE and AE, you can find AD using Pythagoras theorem. So I started from there. We have to find AD. AD is the side of this triangle ADE. And this triangle ADE is a right angle at E, because angle in a semicircle is a right angle. So AD is the hypotenuse. So to find AD, you need to know the legs AE and DE. So find AE and DE and then find AD using Pythagoras theorem. So that's what we have worked earlier. So you always need to have an idea, and then, like now the idea is to find DE, the idea is to find AD using the right triangle ADE, for which we need to find DE and AE. So do that first. So that preparation has to be done first. Now to find DE, it's fine to find BD because BD is equal to DE. So find BD, and BD can be found using this right triangle, because OD is Yeah, OD is 8. And you know, OA is 13. Radius. OA is 13. So OB is also 13. OA radius 13. So OB radius 13. So in this right triangle, you know, the hypotenuse is 13 and this side is 8. So you can find BD. And once you find BD, the same is DE. So we found DE. Next is to find AE. AE. See, you can also find AE using midpoint theorem, children. I have found AE using similarity. You can also find AE using the midpoint theorem. See this triangle. In this triangle, D is the midpoint of BE. O is the midpoint of BA. So the line segment joining the midpoints is parallel to the third side and equal to half the length of the third side. Now this one is 8, so this has to be 16. The line segment joining the midpoints of any two sides of a triangle is parallel to the third side and equal to half the length of the third side. So if OD is 8, AE is 16. You can find AE using the midpoint theorem like this. D is the midpoint of this side because perpendicular from the center to the chord bisects the chord, no? So D is the midpoint of BE. And then AB is the diameter. AB is the diameter. So this is the center of the circle, right? OB is equal to OA. O is the midpoint of the diameter. So since you know the midpoints of two sides of the triangle, this is the triangle. D is the midpoint of B. O is the midpoint of BA. So the line segment joining the midpoints. DO is the line segment joining the midpoints. DO is the line segment joining the midpoints. It's parallel to the third side of the triangle, AE. Is parallel to the third side and equal to half the length of the third side. So OD is 8 centimeters, which means AE is 16 centimeters. What you see here is we found AE using similarity. Prove that the two right triangles are similar. Prove that right triangle BDO is similar to the right triangle BEA. Because common angle and right angle. So they're similar, write the proportion and you get A is 16. And here you can substitute root 105 and twice root 105 also, children. See, I've written, because D is the midpoint, I've written BD and twice BD. You can also write, we found BD, no, already. We found BD. BD is 105. So you can write root of 105 divided by BE is twice root of 105. No, because 105 plus, sorry, square root of 105 plus square root of 105. So it amounts to the same. You can write this, or what I had written earlier was I wrote BD and BE. I wrote twice BD. Both are fine. So like this, we find AE and then we find AD using Pythagoras theorem. So this is 90 degrees because this is the diameter. Angle in a semicircle is a right angle. Angle in a semicircle is a right angle. And then OD is a radius to the inner circle. BE tangent to the inner circle. Radius tangent at the point of contact perpendicular to each other. Now, when you consider BE as the chord to the outer circle, the perpendicular from the center to the chord bisects the chord. So BD is equal to DE. Now, the idea is to find AD using the right triangle ADE. Find AD using the right triangle ADE. So we need to find DE, we need to find AE. Then we can use Pythagoras theorem and find AD. So AE we found using similarity, or you can find using midpoint theorem. But before you do that, you'll have to find BD using Pythagoras theorem. Because in this right triangle, it's given that OA radius is 13. So this one OB is also 13. OD is 8. So you can find BD using Pythagoras theorem. And BD is equal to DE. So you found DE, and then you can find AE using similarity or midpoint theorem. And then find AD using Pythagoras theorem in right triangle or using right triangle AED. Yeah. Next one. So going down to 9th standard, the angle subtended by an arc at the center is double the angle subtended by the same arc at any point on the remaining part of the circle. Arc AQ makes angle AOQ at the center. The same arc AQ makes angle ABQ on the circumference. AQ, AOQ, AQ, ABQ. From the name you can make out AOQ, ABQ. Angle AOQ, angle ABQ. AOQ is made by the arc AQ at the center. Angle ABQ is made by the same arc AQ at the point B on the circumference. The angle at the center is more. Center is double. Circumference is half. When you name the angles, you can make out. This angle is called angle AOQ. So this angle is made by the arc AQ at the point, sorry. So this angle is made by the arc AQ at the center. Now this angle is called angle ABQ. ABQ or ABT? See, ABQ, ABT, correct. Okay, so it's made by the arc. Sorry, this angle is angle A. Somebody is distracting me. I'm sorry, children. Yeah. Excuse me. Yeah, children. So we were talking about AOQ made by arc AQ at the center. ABQ made by the same arc AQ at B on the circumference. So if this is 58, this is 29. Half. Circumference is half. And this is 90. Radius tangent perpendicular. So you can find angle A using angle sum property. In triangle ABT. In triangle ABT, you can find angle A using angle sum property because this is 90 degrees. This is 29. So you can find A. Yeah, take a screenshot, children. No, I think I'll be sharing the presentations with you. So don't worry, I'll share the whole presentation. Yeah. So here, E is the external point, right? E is the external point. So we have EA equal to EC. And E is also the external, E is the external point to both the circles. So EA is equal to EC, and then EB is equal to ED. So EA plus EB is equal to AB equals EC plus ED is CD. Just make sure you write it. See, you need to prove AB, right? AB is equal to CD. What is AB made up of? AB is AE plus. You need to prove that AB is equal to CD. AB is what? AE plus EB. So write it one below the other and then write the result. AB is AE plus EB. So now write what is AE equal to? AE is equal to CE. Tangent from the external point of the circle. And EB is equal to ED. Add both. AE plus EB, AB equals CE, ED, CD. So if angle PRQ is 120 degrees, this angle, this whole angle PRQ, this one is 120 degrees. So if this is 120, so we know this will be 60 and 60 because equal tangents are equally inclined. See, it's a figure like this, children. This angle, this angle. So if this angle is 70, it's going to be 35 here and 35 here, right? Similar situation. These are the two tangents from the external point R. This angle PRQ is 120. So it will be 60 here and 60 here. Okay. So let's join OP and OQ to see some triangles. And we know that this is 90 because radius perpendicular to tangent. And in this triangle, this angle is 60 degrees. See, earlier in the figure, nothing, we wouldn't be able to do anything because no triangle, nothing was there actually. We only had line segments. So we join OP and OQ. So now we see two triangles. And also this is 90 degrees because radius perpendicular to tangent. Take any one of the two triangles. Any one of the two triangles. Okay, so in this triangle, look at the line segments in the result. OR, PR, RQ. OR, where is OR? This one is OR. Okay. PR. Okay, this is PR. And RQ. This is RQ. Okay, now that we have taken this triangle, so OR, PR. Don't worry, RQ, because we know that PR is equal to RQ, no? Because the tangents from the external point. R is the external point. We know that RP is equal to RQ. RP is equal to RQ. Tangents from the external point R to the circle, they are equal. So we have, in the result, we have OR. Then we have PR, this one. And we have RQ. No worries. That means it's like PR plus PR only. Okay. So we'll take up this triangle. Or we need to connect this side OR and this side PR. We know that this is 60 degrees. And since it's a right triangle, you can use trigonometry. Now use trigonometry and connect this side and this side. Because these are the two sides we have in the result. So then it will be cos 60 degrees. Cos 60 degrees is equal to adjacent PR by hypotenuse QR. See, we are intentionally using cos because we need to use a suitable trigonometric ratio to connect PR and OR, which we have in the result, PR and OR. So for 60 degrees, PR is the adjacent side and OR is the hypotenuse because it's opposite of the right angle. So cos 60 degrees is equal to adjacent side PR by the hypotenuse QR. Oh, sorry, OR. Oh my God. Not QR, children, by mistake, sorry. So cos 60 degrees is equal to adjacent side. Since I made that mistake, no, I just want to repeat. So So in right triangle OPR or ORP, cos 60 degrees is equal to adjacent side PR by the hypotenuse OR. See, we have these two line segments in the result. Cos 60 is 1 by 2 equals PR by OR, cross multiply, OR is equal to twice PR. We sort of got the result. OR is equal to, we have got. OR is equal to twice PR we have. So OR is equal to PR plus PR. And OR is equal to PR plus, for another PR, you can write RQ. Because PR, RP is equal to RQ, right? Tangents from the external point R. Is this fine, children? I'll share the presentation, so don't worry. You don't have to take a screenshot and write now or write now. So here you can find AB using, you can find AP using Pythagoras theorem and double AP to get AB. You'll have to also find CD. Now we know that chords that are equidistant from the circle are equal. Chords that are equidistant from the center are equal in length. 9th standard. Circle, chord, center, perpendicular distance from the center, perpendicular distance from the center. If this distance is equal to this distance, see, this one is not the radius. This is not the radius. It's not the radius. So if the perpendicular distance from the center are equal, then the chords are equal in length. Conversely, if the chords are equal in length, then their distances from the center also will be equal. Equal chords are equidistant from the center. Chords that are equidistant from the center are equal. If two chords are equal in length, if the length of this chord is equal to the length of this chord, then the distance of this chord from the center, distance is always perpendicular distance. If these two chords are equal in length, then the perpendicular distance of this chord from the center will be equal to the perpendicular distance of this chord from the center. Conversely, if the distance of these two chords from the center are equal, if this distance is equal to this distance, then the chords are equal in length. So here you can find by Pythagoras theorem, this is 8, so this is 8. So AB is 16. AB is 16. Now, OP is the perpendicular distance. OP is the perpendicular distance of the chord AB from the center. And for OQ, just join this point of contact, Q to O. And this will be 90, right? Because radius tangent at the point of contact perpendicular, this is 90. And how much is this radius? No, so 6. So you can see that OP, OQ, radius of the circle. And they are the perpendicular distances of the chords from the center. So that means chord AB is equal to chord CD because their distance from the center are equal. So AB is 16 centimeters, CD is also 16. See, what may be a little tricky or confusing or, like maybe when, not so clear, maybe now, because AB is a chord to the outer circle and a tangent to the inner circle. In the same way, CD, it's a chord to the outer circle, tangent to the inner circle. So 90 degrees we get by treating the line segments as tangents to the inner circle. And chord is when we treat the line segments with respect to the outer circle. So 90 degrees we get because tangents to the inner circle. So this is 6 radius. This is also 6 radius of the inner circle. So you see that the distance of the two chords from the center are equal. So the chords are equal in length. So AB is 16, 8 plus 8, 16. So CD is also 16. So this is 90. This one is 90 because radius tangent perpendicular this is 90. So 90 minus 50, this is 40. Now this one is an isosceles triangle because OP radius, OQ radius. So this side is equal to this side. So if this is 40, this is also 40. So 180 minus 80, this one is 100 degrees. POQ is equal to 100 degrees. This is 90. Radius tangent perpendicular. This is 90. But this one is 50. So 90 minus 50, 40. This side is equal to this side, radius. So this angle is also 40 degrees. 40 plus 40, 80. 180 minus 80, 100. POQ is equal to 100. Again, OQ is equal to OP. OQ is equal to OP radius. So this side is equal to this side. So this angle is equal to this angle. 180 minus 70, 110. So it will be 55 here and 55 here. Now we need to find angle QPT. QPT is this angle. QPT, this angle. This full angle is 90 degrees. This angle is 90 degrees. This one is 90. But this one is 55. We just found this is 55. So this angle QPT, will be 90 minus 55, 35. This one is 90, this full angle. TPO is 90. Radius tangent perpendicular. This one is 90. But this we just found is 55. So 90 minus 55 is this angle, 35. QPT is 35. In this figure, to find the area of the quadrilateral, you can find the area of one triangle and double it. To find the area of the quadrilateral, find the area of one triangle, half base into height. Find the area of one triangle and double it to find the area of the quadrilateral. You're given this side and this side. So using Pythagoras theorem, you can find PQ. And half into base into height, half into base OQ into height PQ will give you the area of this triangle. Double it, you will get the area of the quadrilateral. So find angle PAB. So since PA equals PB, tangents from the external point P to the circle are equal. So PAB is an isosceles triangle. PA is equal to PB. So this angle is equal to this angle. So 180 minus 60, 120. So it will be 60 here and 60 here, which means PAB is equiangular. You can see each angle is 60 degrees. So PAB is equiangular, which means it's also equilateral. So AB is equal to 5 centimeters. AB is equal to 5 centimeters. We'll have to find the length of the chord AB. So AB is equal to 5 centimeters because the triangle is equilateral. So sometimes you may not be asked to find, this angle. Straight away find AB. given this figure, find AB. All right, so given this figure, find AB. So since these two sides are equal, 180 minus 60, 120, 120 by 2, 60, 60. So triangle PAB is equiangular, so it's equilateral. So all sides are equal, hence AB is 5 centimeters. Children, kindly bear with me for another 5 to 10 minutes. We'll wind up the session. I'll share this presentation with you. Yeah. So these to answer, numerical questions from this chapter circles, you need to have all the theorems in your mind. 9th standard and mostly 9th standard actually. Now this year, what you've learned is what we just learned in this session is angles in the alternate segment of a circle are equal. The rest of it are all of 9th standard. Angle at the center is double the angle on the circumference. Angle in a semicircle is a right angle. Then when you see parallel lines, alternate angles equal, corresponding angles equal. So this here, yeah, radius, tangent, perpendicular to each other. Then if it's an isosceles triangle, whenever you have two radius, so circle, and you have a figure like this. So this is radius, this is radius. So this one is an isosceles triangle. So these two angles are equal. So you must have, like all these theorems must come rushing in your mind. Only then you can, try these numerical sums correctly. So with that, I don't think this should be difficult for you to understand. I told you I'll be sharing the presentation. So I think you can help yourself with this one. We've seen all the theorems needed for these children. Just try this one. So you can see here, chord, tangent. Chord PQ, tangent AB, and through the endpoint P of the chord, we have the tangent AB. And this is the angle between the chord and the tangent. So this angle is equal to, take the chord. This is the alternate segment. Okay, so this one is alternate segment. You can see the point R on the circumference of the alternate segment. And you can see the ends of the chord are joined to R, Q to R, P to R. So this is the angle made by the chord in the alternate segment. So if this is 58, this is also 58. And then this is 90. Angle of semicircle is a right angle. So now you can find PQB using angle sum property. You can find PQR, and that is what is PQB also. You need to find PQB, right? PQB, which is PQR, this angle. This is 90 degrees. The angle in a semicircle is a right angle because it's the diameter. It passes through O. It passes through O. This is the diameter. P is a point on the circumference. So see here, join the ends of the diameter to P, Q to P, R to P. So this is angle in a semicircle is a right angle. This should be the diameter, and the ends of the diameter are joined to the point P on the circumference. That's how we identify angle in a semicircle. So this is 90, and this one is 58 by the alternate segment theorem. So you can find this using the angle sum property. AQB. AQB, this angle. AQB is this angle. Okay, so maybe if we prove that these two triangles are congruent, you can find this angle and double it to get this angle, to get the whole angle. Okay, so let's see how to, now this angle we can find easily because this is the radius, this is the radius, this is the tangent, so this is 90. So 90 minus 70, this is 20. This one is 20. So the answer is 40. The thing is, we'll have to show that these two are congruent. Okay. Yeah, this is 90, right? This is 90. So parallel line, transversal, parallel line. So if this is 90, this is also 90. Alternate angles are equal. See, a parallel line, transversal, parallel line. This is 90. So this is also 90. Alternate angles are equal. So this is also 90. So now it becomes easy to show that the triangles are congruent. 90, 90. So in these two triangles, and again, this is a perpendicular from the center to the chord. So it bisects the chord. So this one is equal to this one. Yeah, so now it becomes easy, right? In the two triangles, this one is the common side. This is the common side. 90 here, 90 here. And then this segment is equal to this segment. So by the SAS congruence criterion, the two triangles are congruent. CPCT, we have this angle equal to this angle. This is 20, so this is also 20, so 40. AQB is 40. AQB is 40. OQ is the radius. This is the tangent. So this is 90. 90 minus 70, this is 20. So we just guess, this also should be 20. If these two are equal, these two angles should be equal. So 20 plus 20, 40 is the answer. Angle AQB is 40 degrees. But we have to show that these two triangles are congruent for that. Parallel line, transversal, parallel line. This is 90. Alternate angles are equal. So this is 90, which makes this also 90. So now these two triangles are right triangles. These two triangles are right triangles. And also perpendicular OL. Perpendicular OL from the center to the chord bisects the chord. AB is the chord. AB chord. OL is the perpendicular from the center to the chord. So it bisects the chord. So AL is equal to BL. AL is equal to BL. This L, this one. AL is equal to BL. So in the two triangles, AL of this triangle is equal to BL of this triangle. 90 here, 90 here. And then LQ is the common side. LQ is the common side. SAS, they are congruent. CPCT equal. So 20, 20, 40. OB, OP, always look out for always see if the triangle has two radii in it, because that makes it isosceles. So you can see this triangle BOP, OB, OP, radius, OB, OP, radius. So if this is 30, this is also 30. Now this is 60. Exterior angle is equal to the sum of the two interior opposite angles. Or you can find this one. You can write 60 straight away here because 30 plus 30 is 60 exterior angle. Or you can find this one 120 and then linear pair 60. Now this is 90. Radius tangent perpendicular. So now you can find OTP, angle sum property. Radius, isosceles triangle. 30, 30, isosceles triangle property. So this is 120. Linear pair 60. Or directly you can write 60 exterior angle property. Exterior angle is equal to the sum of the two interior opposite angles. Okay, 60. Now this is the radius. OP is the radius. PT tangent 90 degrees. So in triangle OPT, in this triangle OPT, 90 degrees, 60 degrees. So you can find this using angle sum property. 90, 60, 150. So this is 30. OTP 30 degrees. Yeah, this we just understood in the class today. So there's a numerical version. We understood the result. We proved that AP is equal to half perimeter of triangle ABC. AP is equal to half perimeter of triangle ABC. So this is a numerical question based on this result. So you'll have to substitute the values and find whatever is asked. This is simple, just using Pythagoras theorem 2 times. OA is given 5, OB 3, PA 12, PA 12. So this is 90, no? Radius tangent, and here tangent radius, this is 90. So this is the hypotenuse. This is the hypotenuse. So 512, hypotenuse is 13. Now for BP, this is not the hypotenuse. 13 is the hypotenuse. So find BP. And don't mistake PA equal to PB, because PA is a tangent to the outer circle, but PB is a tangent to the inner circle. So PA is not equal to PB here. In this figure, PA is not equal to PB because PA is a tangent to the outer circle, but PB is a tangent to the inner circle. Tangents from an external point to the same circle are equal, not to two different circles. Tangents from an external point to the same circle are equal. So here PA is not equal to PB because they are tangents to two different circles. So you can find the hypotenuse using 5 and 12. This is 13. Now in this right triangle, the hypotenuse is 13, this side is 3. So you can find BP again using Pythagoras theorem. But be careful, this is not the hypotenuse, is what I'm saying. So children, this is 90. Radius tangent perpendicular. So this is 30. If this is 30, this is 30. Isosceles triangle, because OS is equal to OR. OS is equal to OR. This is 90. Radius tangent perpendicular. A part of it is 60. So the rest of it is 90 minus 60, 30. If this is 30, this is 30, because OR is equal to OS. Isosceles triangle property. In the same way, this is 90. Radius OQ tangent 90. 90 minus 50, this is 40. This is also 40. So QSR, angle QSR is equal to 40 plus 30, 70 degrees. So for this, you'll have to join OR, OQ, OS. OR radius, RM tangent, 90. So this one is 30. So this is also 30. OSR is an isosceles triangle with OS, OR radius. So they're equal. Here, OQ radius, QL tangent. So this is 90. From the radius to the tangent is 90 degrees. From the radius to the tangent is 90 degrees. So 90 minus 50, this is 40. Again, isosceles triangle because OQ is equal to OS, radius. So this is 40. 40 plus 30, 70. QSR is 70 degrees. Find the perimeter of quadrilateral ABCD. Find the perimeter of quadrilateral ABCD. So you have proved this result in the one of the exercise questions in NCERT, that when a quadrilateral circumscribes a circle, the sum of the opposite sides are equal. There the question is not given in words. So sometimes you will have to remember this in words. When a quadrilateral circumscribes a circle, the sum of the opposite sides are equal. When a quadrilateral circumscribes a circle, the sum of the opposite sides, the sum of the opposite sides are equal. So which are the opposite sides of the quadrilateral? AB, CD, and AB, CD, one pair of opposite sides. Then BC, AD, another pair of opposite sides. The sum of the opposite sides. So AB plus CD, BC plus AD, they are equal. The sum of the opposite sides are equal. You have proved this result. It's a simple proof also. Opposite sides AB, CD, their sum. Opposite sides BC, AD, their sum, equal. Understand this one, children? Understand the result?
Yes, ma'am.
Yeah. So now see here. Just a minute, children. Yeah, apply that result to this question. Just 2 minutes, I'll come back. Yeah, children, yeah. So the result is AB plus CD is equal to BC plus AD. You don't have to prove it. You can use the result. This is mostly MCQ. AB plus CD. See, you can see a quadrilateral circumscribing the circle. ABCD is a quadrilateral that circumscribes the circle with center O. So this result is true. AB plus CD is equal to BC plus AD. So AB is 4 plus CD is 8, BC is 7 plus AD. So like this, you can find AD. Work this and you can find AD. 3 sides of the quadrilateral given, you should find the fourth side. Okay. This one you can help yourself. It is simple. Maybe I can do it fast. So this is 4, this is 3, this is 5, and this is 6. And you know how to find the perimeter. 4 plus 3 plus 3 plus 5 plus 5 plus 6 plus 6 plus 4. This, I think, in one of the classes recently, we did a question like this, finding the value of R. Yeah. Now again, this one, the proof to a question like this, we have, you have seen in NCERT. When a quadrilateral circumscribes a circle, the opposite sides subtend supplementary angles at the center. The opposite sides, I think it's the last one. Second exercise, last proof, if I'm not wrong. When a quadrilateral circumscribes a circle, the opposite sides subtend supplementary angles at the center. That is the angles subtended by the opposite sides. They are supplementary. Here, okay, you can see A, B, C, D. 1 minute. Is this figure correct? 1 second. Where is the quadrilateral? Oh, okay. No. This is not relevant, this figure, children. Ignore this figure. Oh, I put this by mistake. Anyways, no. I didn't intend this figure, children. So this is the intended figure. Sorry. Okay, so like this. Quadrilateral A, B, C, D, like this, children. I'm sorry if I confused you. Okay, we are talking what I said is true. This figure is not appropriate to what we are discussing. Yeah, so you can see quadrilateral ABCD circumscribes the circle with center O. Now the opposite sides of this quadrilateral will subtend the supplementary angles at the center. Now AOB is the angle subtended by the side AB at the center. Angle COD is the angle subtended by the side CD at the center. Now the sum of these two angles is equal to 180. These two angles are supplementary. So if this is 85 degrees, this one will be 180 minus 85, 95 degrees. Otherwise, you cannot find. Without this property, you cannot find the measure of X. See, this one is X, no? You cannot find X. Quadrilateral. It circumscribes a circle. The quadrilateral circumscribes a circle. Circle with center O. You can see the quadrilateral outside it. We also say that the sides of the quadrilateral are tangential to the circle. We also say the sides of the quadrilateral are tangential to the circle. AB is a tangent to the circle. BC is also a tangent to the circle. CD is a tangent to the circle. AD is a tangent to the circle. So when a quadrilateral circumscribes a circle, we say that the sides of the quadrilateral are tangential to the circle. Okay. So one result we saw was that the sum of the opposite sides are equal. In a situation like this, the sum of the opposite sides are equal. AB plus CD is equal to BC plus AD. In this situation, the sum of the opposite sides are equal. This is the other result. The opposite sides, they subtend the supplementary angles at the center. The opposite sides. So AD and BC are opposite sides. They subtend angles at the center. This is the angle subtended by the side AD. This is the angle subtended by the side BC. The sum of these two angles will be 180 degrees. Similarly, the sum of this angle and this angle. This is the angle subtended by the side CD at the center, angle COD. And this is the angle subtended by the side AB at the center. This is the angle subtended by side AB at the center, angle AOB. These two angles are supplementary. Opposite angles are supplementary. So x plus 85 is equal to 180 degrees. So x is 180 minus 85, 95 degrees. Again, one of the earlier classes, we understood that AOBP is a cyclic quadrilateral. AOBP is a cyclic quadrilateral. Though we don't see a circle running through the vertices A, B, and P, you understand it is a cyclic quadrilateral because you can draw a circle or there is a circle passing through the vertices A, B, and P. AOBP is a cyclic quadrilateral because this is the proof. This is 90, this is 90. This is 90, this is 90. One pair of opposite angles supplementary. Therefore, AOBP is a cyclic quadrilateral. So that means x plus 30 is also 180. X plus 30 is 180. So like that you can find x. X plus 30 is 180. So this is by the result. We just discussed this. Quadrilateral circumscribes a circle. The sum of the opposite sides are equal. AB plus CD is equal to BC plus AD. Here, same situation like this. Quadrilateral circumscribed circle. This figure is not correct. But the result is the opposite sides subtend the supplementary angles at the center. The opposite sides of the quadrilateral will make supplementary angles at the center. X plus 85 is equal to 180 degrees. Okay. Class, use the emoji. Raise your hand. Raja, Krishmi, Madhumita, Krish, Arjun, and Sashank. Okay. All right, children. So with this, we have discussed all the important questions from the chapter circles. So next class, we'll do some important questions from probability. And after that, we'll start revising for the board exam. We'll start working question papers. We'll solve question papers and practice for the board exam. So I think next 2 sessions we'll do probability. And then we'll, start the revision for the board exam. All right, children. So that's it for today's session. I'll share the 2 presentations from which we discussed the sums today. Please, go through the presentation. It's okay. They're too simple to work actually. So it's enough if you just have a look at the presentation. I'll also share the recording. You can, go through the recording or go through the presentation. Both are the same. All right, children. So that's it for today's session. Thank you so much. You may leave the call.
Thank you, ma'am.
Thank you.